wabarakatuh. My name is Farhan Akil bin Fazal Azman, and on behalf of the group Transformers in the class of Sir Hisham in Electrical Fundamental 2. So today I will be talking about Transformers. Um, a bit about Transformers. It's the mutual induction and the effect of the rate of change, primary current, and mutual inductance have on induced voltage. So, before we proceed, what is mutual inductance? Mutual inductance is whenever two coils are located so that the flux from one coil links with the turns of the other coil. A change of flux in one coil causes an EMF, electromotive force, to be induced into another coil. This allows the energy from one coil to be transferred or coupled to the other coil. The two coils are said to be coupled or linked by the property of mutual inductance. The amount of mutual inductance depends on the relative positions of the two coils. That's the general form. Apart from that, the voltage can only be induced in the second inductor if the flux of the first inductor that cuts through the coil of the second inductor changes. I repeat, the voltage can only be induced in the second inductor if the flux of the first inductor that cuts through the coil of the second inductor changes. It's either increases or decreases. And also, mutual inductance is the ability of one inductor to induce a voltage in another inductor placed nearby in another circuit. Moving on to the next slide. If the flux increases, the polarity of the induced voltage in the second coil will be in one direction. If the flux decreases, it is vice versa. The polarity of the induced voltage will be in the opposite direction. It's vice versa. Okay, and the magnitude of the induced voltage in the second coil is proportional to the rate of change of the flux through the coils of the second inductor, which is caused by the change of the current through the first coil. So as you can see in the formula given in the slide, the formula, so you guys can refer to it to do any questions or anything. Next, moving on to the next slide. This is also a fun fact it's not a fun fact, it's another more fact that you should know about mutual inductance. Mutual inductance also is the basic operating principle of the transformers, motors, generators, and other electrical component that interacts with another magnetic field. Then we can define mutual induction as the current flowing in one coil that induces a voltage in an adjacent coil. So mutual inductance ni dia ada dekat dia tak semestinya ada di transformers, tapi dia boleh ada di motor and generator also. Okay. The amount of mutual inductance that links one coil to another depends very much on the relative positioning of the two coils, macam saya cakap tadi lah. And if one coil is positioned next to the other coil so that their physical distance apart is smaller, then nearly all of the magnetic flux generated by the first coil will interact with the coil turns of the second coil, inducing a relatively large EMF and therefore producing a large mutual inductance value. So like we letak the first coil and the second coil together, rapat in a closed position, so it will generate a relatively large EMF there between it. So it will also producing a large mutual inductance. And if kita letak jauh, so vice versa lah, dia punya kesudahan dia. And also, another thing, likewise if the macam saya cakap tadi lah, the two coils are farther apart tu, ada from different angles, the amount of induced magnetic flux from the first coil into the second coil is weaker, much smaller indeed. Okay. But there's the but. But mutual inductance can also be a bad thing, as stray or leakage inductance from coil can interfere with the operation of another adjacent. It has a benefit and ada kelebihan dan keburukan mutual inductance. So it has pros and cons. So okay, moving on to the next chapter. At the next slide, mutual inductance between coils. So the slide shows you more understanding. Boleh faham through the slide. There's a diagram there, so you can see through the diagram. Short distance between the first coil and the second coil, and the difference between the large distance of the first coil and the second coil. Okay. And there's a formula there, so you can do it on questions. Now, we're moving on to the next subtopic, factors that affecting mutual inductance. So, as I can research in the internet, I found that there are 3 factors affecting mutual inductance in general. The first one is the mutual inductance of 2 adjacent coils is dependent upon the physical dimension of the 2 coils. The number of turns in each coil, the distance between the 2 coils, the relative position of the axis of the 2 coils, and the permeability of the cores. The second one is the coefficient of coupling. Okay, this is a new term, the coefficient of coupling. The coefficient of coupling, what is meant by the coefficient of coupling? The coefficient of coupling between 2 coils is equal to the ratio of the flux cutting one coil to the flux originated in the other coil. If the 2 coils are so positioned with respect to each other so that all of the flux of one coil cuts all of the turns of the other, the coils are said to have a unity coefficient of coupling. It is never exactly equal to unity, but it approaches this value in certain times of coupling device. So what do we mean by unity? Unity is 1. We stand as 1, so the value of 1 in the coefficient of coupling. So in real life, so there's no such thing as a perfect time. So tak semestinya kita dapat nilai 1 tu, dia mesti kurang, maybe kurang only, tapi it almost to unity. And if all of the flux produced by one coil cuts only half the turn of the other coil, the coefficient of coupling is 0.5. Macam saya cakap tadi lah, maybe kalau dia cut full, if it is cut full, so it will cause a unity more around to 0.8 to 1, I think. But if you cut half, it will get 0.5. So the coefficient of coupling is designated by the letter K. So K is for the coefficient of coupling. As you can see in the formula, M equals to K power root of L1 and L2. M is for mutual inductance in unit henries. K equals to coefficient of coupling. L1, L2 equals to inductance of coil in the unit of henries. So let's see this sample problem. So I give it, if 110 H coil and 120 H coil are connected in series and are physically close enough to each other so that their coefficient of coupling is 0.5, what is the mutual inductance between the coil? So if we want to find the mutual inductance using the formula, so you have to use the M equals to K. The formula M equals to K power root of L1 and L2. So as you can see here, we need to find M, and K is already given. It is the coefficient of coupling. Coefficient of coupling is 0.5, meaning that the flux produced by one coil only cuts the half of the other coil. Okay, that's why it gets 0.5. So L1, L2, L1 is the coil of number 1. So we take the 10H and L2 is 20H. We put in the value and there we get 7.07 Henry. Okay, moving on to the next slide. Transformer construction principles and operation. I guess I will pass on to my other teammate Ashraf Hakim. So thank you and Assalamualaikum warahmatullahi wabarakatuh from me. Goodbye.
Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Ashraf Hakim bin Rosli. I am from class 2 AVM4. So today I will present to you about the principle of transformer and the operations of to overcome the transformer. So firstly, the basic principle behind working of a transformer is the phenomenon of mutual induction between two windings linked by common magnetic flux. So basically, a transformer consists of two inductive coils, which is primary winding and secondary winding. The coils are electrically separated by magnetically link each other. When primary winding is connected to a source of alternating voltage, alternating magnetic flux is produced. Most of the flux get linked with the secondary winding, which is called as useful flux and mean flux, and the flux which does not get linked with secondary winding is called leakage flux. So as the flux produced is alternating, which is the direction of it is continuously changing, EMF gets induced in the secondary winding according to Faraday's law of electromagnetic induction. This EMF is called mutually induced EMF. If the secondary winding is closed, the mutually induced current flows through it, and hence the electrical energy is transferred from one circuit, which is primary, to another circuit, which is secondary. So after that, the operations of transformer. Basically, transformer consists of two inductive windings and a laminated steel core. The cores are insulated from each other as well as from the steel core. A transformer may also consist of a container for winding and core assembly, which is called tank, and suitable bushings to take our terminals, oil conservator to provide oil in the transformer tank for cooling process and others. I and L. To avoid high reluctance adjoins, laminations are stacked by alternating the sides of joint. This is if joints of first sheet assembly are at front face, the joints of following assembly are kept. So we continue to transformer losses and methods to overcome. So the transformer losses are real. I will explain to you. I will present to you the meaning of transformer losses. Real transform energy losses are dominated by winding, resistance joule, eddy current, and core losses. Transformer efficiency tends to improve with increasing transformer's capacity. The efficiency of typical distribution transformer is between 98% to 99%. In any electrical loss can be defined as the difference between input power and output power. An electrical transformer is an static device, hence mechanical losses like windage or friction losses are absent in it. A transformer only consists of electrical losses, which is iron losses and copper losses, the two things losses. Transformer losses are similar to losses in a DC machine, except that transformer do not have mechanical losses. Losses in transformer are explained below, which the first is core losses, or we call it no load losses, core losses or iron losses, which is no load losses. Eddy current losses and hysteresis loss depends upon the magnetic properties of the material used for the construction of core. Hence, the losses are also known as a core losses or iron losses. So second is hysteresis losses in transformer, which is the core losses. Hysteresis loss is due to reversal magnetization in the transformer core. This loss depends upon the volume and grade of the iron, frequency of magnetic reveals, and value of flux density. It can be given by Steinmetz formula. So I'll explain to you the eddy current loss in transformer, which is the core losses. In transformer, AC current is supplied to the primary winding, which is setups alternating magnetizing flux. When the flux linked with secondary winding, it produces induced EMF in it, but some part of the flux also get linked with other conducting parts like steel core or iron body or the transformer, which will result in induced current, induced in EMF in those parts. This current is called eddy current. Due to the eddy current, some energy will be dissipated in the form of heat. So the third one is iron losses, which is no load losses. No load losses occur in the core material due to hysteresis and eddy current, and are present almost continuously while the transformer is connected to the electricity supply. So we continue with the methods to overcome the core losses, which is eddy current losses within a transformer core cannot be eliminated completely, but they can be greatly reduced and controlled by reducing the thickness of steel core. Instead of having a big solid, iron core as the magnetic core material of the transformer, or called the magnetic path, is split up into many thin pressed steel shapes called lamination. And the last one, the losses of energy, which appears as heat due both to the hysteresis and to eddy currents, is the magnetic path, which is known as transformer core losses. So the second one is methods to overcome the copper losses. Transformer with high voltage and current ratings require conducts of large cross section to help minimize their copper losses. Increasing the rate of heat dissipation is one of the methods for better cooling by forced air or oil, or by improving the transformer insulation so that it will withstand higher temperature and also increase transformer voltage rating. So that's all from me. Thank you.
Assalamualaikum warahmatullahi wabarakatuh. My name is Yasmin Farzana binti Omar. I'm from class 284. I will explain about transformer action under no load condition. In a practical transformer, there are losses in the primary due to resistance, hysteresis, and eddy current. When a voltage is applied to the primary with no load connected, the primary alternating flux will also induce a back EMF into the primary winding in opposition to the applied EMF. When the transformer is operating at no load, the secondary winding is open circuit, which means there is no load on the secondary side of the transformer. Therefore, current in the secondary will be zero, while primary winding carries a small current called no load current, which is 2 to 10% of the rated current. A very small current that flows in the primary is a current which is necessary to overcome losses and to magnetize the core. This current is responsible for supplying the iron losses like hysteresis and eddy current losses in the core, and a very small amount of copper losses in the primary winding. The angle lag depends upon the losses in the transformer. The power factor is very low and varies from 0.1 to 0.15. Primary voltage and secondary voltage are in antiphase. A float primary current will lag behind the primary voltage. The no-load current consists of two components. The first one is reactive or magnetizing component. It is in quadrant with applied voltage. It produces flux in the core and does not consume any power. The second is active or power component, also known as a working component. It is in phase with the applied voltage. It supplies the iron losses and a small amount of primary copper loss. Next, I will explain about transformer action with load condition. On connecting a load to the transformer, a current will be set up in secondary winding and a flux will be produced. So, secondary current provides a flux in the core which is opposite the primary flux. It will reduce the total flux in the core. Then, primary back EMF is reduced. The secondary flux opposes the primary flux and effectively decrease the primary inductance. If the applied voltage is kept constant, the decrease in the inductor result is an increase in the primary current. This increase in current is known as the load component of primary current. So, effective EMF in the primary increase, so does the primary current. The load current is in the primary set up flux that is equal and opposite to the secondary flux. The ampere turns of the primary flux equal to the ampere of the secondary flux. Increased loading on the secondary increase the primary current. The total primary current is the vector sum of the no-load current and the load current. As the secondary current increases, so primary current will increase. Under normal condition, the load current is so much larger than the no-load current that the latter can be ignored. Next, I will explain about power transfer. Power transfer is an ideal power transformer is a device that neither produce nor store or consume any energy. All it does is transfer the power from the power network to the load by changing the primary and secondary voltage in accordance to the phase-turn ratio. However, the power cannot be transferred completely because of the core loss and copper loss. In a transformer, as long as the primary is connected to voltage sources, the secondary will induce an output voltage. If the losses are ignored, the power in the secondary equal to the power in the primary. Alright, I will move on with efficiency. A transformer does not require any moving parts to transfer energy. This means that there are no friction or windage losses associated with the other electrical machine. However, transformers do suffer from other type of losses called copper losses and iron losses, but generally these are quite small. The efficiency of a transformer formula is output power over input power times 100%. The intensity of power loss in the transformer determines its efficiency. The efficiency of a transformer is reflected in a power loss between the primary and the secondary winding. The resulting efficiency of transformer is equal to the ratio of the power output of the secondary winding to the output to the power input of the primary winding, therefore is high. An ideal transformer is 100% efficient because it delivers all the energy it receives. Real transformer, on the other hand, are not 100% efficient because it will lose. Real transformer, on the other hand, are not 100% efficient and at full load. The efficiency of transformer is between 94% to the 96%, which is quite good. For a transformer operating with a constant voltage and a frequency with high capacity, the efficiency may be as high as 98%. Due to transformer losses, the output power is always less than primary power. The next is polarity marking. Polarity marking is important of essential to correctly construct three-phase transformer banks and to properly parallel single or three-phase transformer with existing electrical system. A knowledge of polarity is also required to connect potential and current transformer to power metering device and protective relay. The basic theory of additive or subtractive polarity is underlying principle used in step voltage regulator, where the series winding of an auto transformer is connected to either buck or boost the applied line voltage. Transformer polarity refers to the relative direction of the include voltage between the high voltage terminal and the low voltage terminal. During the AC half cycle, when the applied voltage or in the case of a current transformer, is from H1 to the H2 of the secondary induced voltage direction will be from S1 to S2. In practice, polarity refers to the way the leads are brought out of the transformer. Polarity mark is to ensure correct wiring. Polarity marks are shown on the instrument connection diagram, control schematic, and three-line power diagram. The polarity mark is usually shown as a round dot or an adjacent to H1 and S1 terminal, or PT and CTs, sometimes alternate marking in the form of a square dot, slash mark, or plus or sign or minus sign will be used to identify the polarity terminal on electrical drawing. Instrument transformer may also have the terminal identified with polarity mark. If instrument transformer do not have polarity marks on them, it is understood that the H1 as primary and the S1 as the secondary terminal are polarity. Polarity is not a consideration on single element device such as an ammeter or voltmeter, but it is essential for proper operation of power measuring device and for directional or differential protective relay. That's all for me. The next point my friend will explain. Thank you.
Okay, hi sir. Assalamualaikum. My name is Muhammad Azadi bin Mazlan and I'm from 2AVM4. Okay, I'm grouped with Farah Nakil, Ashraf, Yasmin and Natasha, and our group will present about transformer. Okay, so I will explain about primary and secondary current, voltage, turn ratio and power. Okay, so first step up and step down transformer. Bismillahirrahmanirrahim. Okay, this is very useful device. We can easily multiply or divide voltage and current in AC circuits. The transformer has made the long distance transmission of electric power, as AC voltage can be stepped up and current stepped down for reduced wire resistant power losses along power lines connecting generating stations with loads. At either end, both the generator and at the loads, voltage levels are reduced by a transformer for safer operation and less expensive equipment. A transformer that increases the voltage from primary to secondary, in bracket, more secondary winding turns than primary winding turns, is called a step-up transformer. The ratio of secondary voltage to primary voltage is equal to the ratio of the number of turns in the secondary winding to the number of turns in the primary winding. So the formula is secondary voltage divide primary voltage equals to secondary turns, one number of turns, and primary number of turns. If there are more turns on the secondary than on the primary, the turn ratio is greater than 1. A transformer designed to do just the opposite is called a step-down transformer, which the secondary voltage is less than the primary voltage. The amount by which the voltage is stepped down depends on the turn ratio. The turn ratio of a step-down transformer is always than 1. Transformer step up or step down voltage according to the ratios of primary to secondary turns. So the voltage transformation ratio equal to secondary number of turns divided by primary number of turns. and current transformation ratio is equal to primary number of turns divided by secondary number of turns, where n is the number of turns in winding. A transformer designed to increase the voltage from primary to secondary is called step-up transformer. A transformer designed to reduce the voltage from primary to secondary is called a step-down transformer. So next is current transformer. To find the primary and secondary current of a transformer is by using Vs divided by Vp equal to Ns divided by Np, where Vs is the secondary voltage, Vp is the primary voltage, Ns is the number of secondary windings, and Np is the number of primary windings. Divide the number of secondary windings by the number of primary windings and multiply the source voltage by the ratio. So current transformer is a type of instrument transformer that is designed to produce an alternating current in its secondary winding, which is proportional to the current being measured in its primary. Current transformer reduce high voltage currents to a much lower value and provide a convenient way of safely monitoring the actual electrical flowing in an AC transmission line using a standard ammeter. So, primary and secondary current. The current in the secondary is the current in the primary, in bracket, assuming a single turn primary, divided by the number of turns of the secondary. The primary current of a current transformer is not dependent of the primary current of a current transformer is not dependent of the secondary load current, but instead is controlled by an external load. The secondary current is usually rated at a standard 1 ampere or 5 ampere for larger primary current ratings. So primary current. The current transformer consists of only one or very few turns as its primary winding. This primary winding can be of either a single flat turn, a coil of heavy duty wire wrapped around the core, or just a conductor or bus bar placed through a center hole as shown, which is in the slide. It's like just like a square thing and there's a hole in the middle. Due to this type of arrangement, the current transformer is often referred to as a series transformer, as the primary winding, which never has more than a very few turns, is in series with the current carrying conductor supplying a load. So secondary current. The secondary winding, however, may have a large number of coil turns wound on a laminated core of low-loss magnetic material. This core has a large cross-sectional area so that the magnetic flux density created is low using much smaller cross-sectional area wire. Depending upon how much the current must be stepped down as it tries to output a constant current independent of the connected load. It will supply a current into either a short circuit in the form of an ammeter or into a resistive load until the voltage induced in the secondary is big enough to saturate the core or cause failure from excessive voltage breakdown. So there are three basic types of current, which is wound current transformer, toroidal current transformer, and bar type current transformer. So first is wound current transformer. The transformer primary winding is physically connected in series with the conductor that carries the measured current flowing in the circuit. The magnitude of the secondary current is dependent on the turns ratio of the transformer. That is wound current transformer. And next is toroidal current transformer. These do not contain a primary winding. Instead, the line that carries the current flowing in the network is threaded through a window or hole in the toroidal transformer. Some current transformer have a split core which allows it to be opened, installed and closed without disconnecting the circuit to which they are attached. So bar type current transformer. Next is bar type current transformer. This type of current transformer use the actual cable or bus bar of the main circuit as the primary winding, which is equivalent to a single turn. They are fully insulated from the high operating voltage of the system and are usually bolted to the current carrying device. Okay, next is voltage. A potential transformer, in bracket PT, is typically expressed in primary to secondary voltage ratio. For example, in a ratio of 600 to 120 PT will mean the voltage across secondary is 120 volts when primary voltage is 600 volts. Voltage transformer VT, also called potential transformer, so is designed to present negligible load to the supply being measured and have an accurate voltage ratio and phase relationship to enable accurate secondary connected metering. The voltage transformer can be thought of as an electrical component rather than an electronic component. A transformer basically is very simple static, in bracket or stationary, electromagnetic passive electrical device that works on the principle of Faraday's law of induction by converting electrical energy from one value to another. Transformer increased voltage. Transformer converts alternating current AC from one voltage to another voltage. It has no moving parts and works on a magnetic induction principle. It can be designed to step up or step down voltage. So, a step up transformer increases the voltage and a step down transformer decreases the voltage. What is primary and secondary voltage? So, primary voltage is the voltage applied to the terminals of the primary winding of a transformer. If the primary has fewer turns than the secondary, you have a step up transformer that increases the voltage. But if the primary has more turns than the secondary one, you have a step down transformer that reduces the voltage. So, primary voltage. Primary voltage is the voltage applied to the terminals of the primary winding of a transformer. It must be in the form of changing voltage, which creates a constantly changing current in the primary, since only a changing magnetic field will produce a current in the secondary. So to find primary voltage, Vs divided by Vp equal to Ns divide Np, where Vs secondary voltage, Vp primary voltage, Ns number of secondary windings, and Np number of primary windings. Divide the number of secondary windings by the number of primary windings and multiply the source voltage by this ratio. So primary voltage, transformer increase primary voltage by keeping its frequency constant. Magnetizing current in the primary transformer increase as it is directly proportional to driving voltage. If magnetizing current goes beyond certain limit, transformer core may saturate. To reduce the primary voltage, first is to insert two 12-volt zeros of adequate current rating in one primary leg of the transformer. This brings the input voltage back down to a reasonable value and the secondaries back into spec. The second method is to add a bucking transformer to the primary and reduce the input voltage. Secondary voltage. Secondary voltage is the coil winding supplying the output voltage. The output voltage of a transformer varies with varying load resistance, even with a constant voltage input. A transformer with a primary winding of 1000 turns and a secondary winding of 100 turns has a turns ratio of 1000 to 100 or 10 to 1. Therefore, 100 volts applied to the primary will produce a secondary voltage of 10 volts. To find secondary voltage, with the turns ratio, the secondary voltage can be determined with the following formula: V sec equal to N in bracket V prime, where V sec is voltage secondary and V prime is voltage primary and N is turn ratio. So, transformer increase secondary voltage. One coil turn on the secondary to one coil turn on the primary. If the output secondary voltage is to be greater or higher than the input voltage, in bracket step up transformer, then there must be more turns on the secondary, giving a turns ratio of 1 to n, in bracket 1 to n, where n represent the turns ratio number. To lower the secondary voltage, you must remove turns from the secondary winding. This will increase the available current, since the power in equal to power out, in bracket neglecting losses. However, as you increase current available, the winding wire must increase in size to accommodate the current without a flame out. So, transformers turn ratio. Transformers are all about ratios. The ratio of the primary to the secondary, the ratio of the input to the output, and the turns ratio of any given transformer will be the same as its voltage ratio. In other words, for a transformer, its turns ratio equal to voltage ratio. So, the transformer turns ratio is the number of turns of the primary winding divided by the number of turns of the secondary winding. It provides the expected operation of the transformer and the corresponding voltage required on the secondary winding. So the transformer turn ratio equal to secondary primary winding, and divide with primary winding. So turn ratio is 10, mean this is step up transformer. If turn ratio is 1/10, mean this is step down transformer. So the simplest meaning, the turns ratio is defined as the ratio of turns of wire in the primary winding to the number of turns of wire in the secondary winding. So primary and secondary turn ratio. A transformer with a primary winding of 1000 turns and secondary winding of 100 turns has a turns ratio of 1000 to 100 or 10 to 1. Therefore, 100 volts applied to the primary will produce a secondary voltage of a 10 volts. The ratio of Vs to Vp or Ns to Np is known as the transformation ratio. So example number 1, a voltage transformer has 1500 turns of wire on its primary coil and 500 turns of wire for its secondary coil. What will be the turns ratio of the transformer? So we're using the formula Np divided by Ns, or Np divided by Ns, which is 500,000, which is 1,500 divide 500 and equal to 3/1, which is 3 to 1. The ratio is 3 to 1. So this ratio of 3 to 1 simply means that there are 3 primary windings for every one secondary winding, as the ratio moves from a larger number on the left to a smaller number on the right. The primary voltage is therefore stepped down in value as shown in the slide. So the main purpose of a transformer is transform voltage at preset ratios, and we can see that the primary winding has a set amount of has a set amount or number of windings on it to suit the input voltage. If the secondary output voltage is to be the same value as the input voltage on the primary winding, then the same number of coil turns must be wound onto the secondary core as there are on the primary core, giving an even turns ratio of 1 to 1. In other words, 1 coil turn on the secondary to 1 coil turn on the primary. Next, if the output secondary voltage is to be greater or higher than the input voltage, in bracket step up transformer, then there must be more turns, the secondary giving a turns ratio 1 to n. Likewise, if it is required that the secondary voltage is to be lower or less than the primary step down transformer, then the number of secondary windings must be less, giving a turns ratio of n to 1. So next is electrical power in a transformer. Another one of the transformer basics parameters is its power rating. The power rating of transformer is obtained by simply multiplying the current by the voltage to obtain a rating in volt amperes. Small single-phase transformers may be rated in volts amperes only, but much larger power transformers are rated in units of kilovolt amperes, in bracket kVA, where 1 kilovolt ampere is equal to 1000 volt amperes. Units of megavolts amperes, in bracket MVA, where 1 megavolt ampere is equal to 1 million volt amperes. So in an ideal transformer, ignoring any losses, the power available in the secondary winding will be the same as the power in the primary winding. They are constant voltage device and do not change the power, only the voltage to current ratio. Thus, in an ideal transformer, the power ratio is equal to 1, as the voltage multiplied by the current will remain constant. That is the electric power at 1 voltage or current level on the primary is transformed into electric power at the same frequency to the same voltage or current level on secondary side. Although the transformer can step up or step down voltage, it cannot step up power. Thus, when a transformer step up a voltage, it step down the current and vice versa, so that the output power is always at the same value as the input power. Then we can say that primary power equals secondary power, in bracket P equal to PS, or P or VPIP cos theta P equal to VS IS cos theta S, where theta P is the primary phase angle and theta S is the secondary phase angle. I think it's theta. Okay, that's all from me. Thank you.
Okay, hi, Assalamualaikum. Before we continue to the next topic in this slide, I would like to introduce myself as Natasha Mira binti Kamar Zaman from 2AVM4, and I will be talking about efficiency and auto transformer plus the facts, interesting facts of transformers. So let's go. Efficiency. The efficiency of a transformer is expressed in percentage. The efficiency of a transformer is reflected in power wattage loss between the primary input and secondary output windings. Then the resulting efficiency of a transformer is equal to the ratio of the power output of the secondary winding, which is in capital P and a small s, to the power input of the primary winding, capital P with a small p, and is therefore high. An ideal transformer is 100% efficient because it delivers all the energy it receives. Real transformers, on the other hand, are not 100% efficient, and at full load, the efficiency of a transformer is between 94% to 96%, which is quite good. For a transformer operating with a constant voltage and frequency with a very high capacity, the efficiency may be as high as 98%. The efficiency of a transformer is given as a picture in the slide. Okay, so for example, if the input power to a transformer is 650 watts and the output power is 610 watts, what is the efficiency? So the solution for this question is efficiency equals to P out over P in times 100. So the efficiency would be efficiency equals to 610 watts over 650 watts times 100. And in the end, we would get 93.8%, so that would be the final answer. Hence, the efficiency is approximately 93.8%, with approximately 40 watts being wasted due to heat losses. Due to transformer losses, the output power is always less than the primary power. So we shall continue. Generally, when dealing with transformers, the primary watts are called volt amps to differentiate them from the secondary watts. Then the efficiency equation above can be modified to efficiency equals to secondary watts in bracket output over primary volt amps in bracket input. Okay, so we shall continue with the next topic, which is autotransformers. An autotransformer is mainly used for the adjustment of line voltage to either change its value or to keep it constant. If the voltage adjustment is by a small amount, either up or down, then the transformer ratio is small, as primary voltage and secondary voltage are nearly equal. Currents, primary current and secondary current, are also nearly equal. Therefore, the portion of the winding which carries the difference between the two currents can be made from a much smaller conductor size, since the currents are much smaller, saving on the cost of an equivalent double wound transformer. However, the regulation, leakage, inductance, and physical size, since there is no second winding of an auto transformer for a given volt amp or kilovolt amp rating, are less than for a double wound transformer. The auto transformer have many advantages over conventional double wound transformers. They are generally more efficient for the same volt amp rating, are smaller in size, and as they require less copper in their construction, their cost is less compared to double wound transformers of the same volt amp rating. Also, their core and copper losses, current and resistance are lower due to less resistance and leakage reactance, giving a superior voltage regulation than the equivalent to winding transformer. The auto transformer has many uses and applications, including the starting of induction motors, used to regulate the voltage of transmission lines, and can be used to transform voltage when the primary to secondary ratio is close to unity. An auto transformer can also be made from conventional two winding transformers by connecting the primary and secondary windings together in series. And depending upon how the connection is made, the secondary voltage may add to or subtract the primary voltage. Before I continue, for the next 3 slides will be an explanation for pictures in the slides. So for the first slide, auto transformer has only one single voltage winding, which is common to both sides. The single winding is tapped at various points along its length to provide a percentage of the primary voltage supply across its secondary load, Then the auto transformer has the usual magnetic core but only has one winding, which is common to both the primary and secondary circuits. Therefore, in an auto transformer, the primary and secondary windings are linked together both electrically and magnetically. The main advantage of this type of transformer design is that it can be made a lot cheaper for the same volt-amp rating, but the biggest disadvantage of an auto transformer is that it does not have the primary or secondary winding isolation of a conventional double wound transformer. The section of winding designated as the primary part of the winding is connected to the AC power source, with the secondary being part of this primary winding. An auto transformer can also be used to step the supply voltage up or down by reversing the connections. If the primary is the total winding and is connected to a supply, and the secondary circuit is connected across only a portion of the winding, then the secondary voltage is stepped down as shown in the picture. Okay, so for the next picture slide, when the primary current is flowing through the single winding in the direction of the arrow as shown in the picture, the secondary current flows in the opposite direction. Therefore, in the portion of the winding that generates the secondary voltage, the current flowing out of the winding is the difference of primary current and secondary current. The auto transformer can also be constructed with more than one single tapping point. Auto transformers can be used to provide different voltage points along its winding or increase its supply voltage with respect to its supply voltage, primary voltage as shown in the picture. Next, the standard method for marking an auto transformer windings is to label it with the capital uppercase letters. So for example, A, B, SAC, and etc. is to identify the supply end. Generally, the common neutral connection is marked as end, capital N, or small n. For the secondary tappings, suffix numbers are used for all tapping points along the auto transformer's primary winding. These numbers generally start at number 1 and continue in ascending order for all tapping points as shown. And for information, the example of the letters capital A, B, and Z, and etc. would be in capital letters. Next would be auto transformers are clearly much cheaper than conventional double wound transformers of the same volt-amp rating. This is done by comparing the amount of copper saved in the winding. If the ratio in bracket small n is defined as the ratio of the lower voltage to the higher voltage, then it can be shown that the saving in copper is n 100%. For example, the saving in copper for the two auto transformers would be shown in the picture inserted in the slide. So next, I will be listing down the disadvantages of auto transformer. The main disadvantage of an auto transformer is that it does not have the primary to secondary winding isolation of a conventional double wound transformer, then cannot safely be used for stepping down higher voltage to much lower voltage suitable for smaller loads. If the secondary side winding becomes open-circuited, load current stop flowing through the primary winding, stopping the transformer action, resulting in the full primary voltage being applied to the secondary terminals. If the secondary circuit suffers a short circuit condition, the resulting primary current will be much larger than an equivalent double wound transformer due to the increased flux linkage damaging the auto transformer. Since the neutral connection is common to both the primary and secondary windings, earthing of the secondary winding automatically earths the primary as there is no isolation between the two windings. Double wound transformers are sometimes used to isolate equipment from earth. With a variable auto transformer, it is used to produce a variable AC voltage from a fixed voltage AC supply. This type of variable auto transformer is generally used in laboratories and science labs in schools and college, and is known more commonly as the variac. The construction of a variable auto transformer will be shown in a picture in the slide. Same as for the fixed type, a single primary winding wrapped around a laminated magnetic core is used as in the auto transformer, but instead of being fixed at some predetermined tapping point, the secondary voltage is tapped through a carbon brush. This carbon brush is rotated or allowed to slide along an exposed section of the primary winding, making contact with it as it moves, supplying the required voltage level. Contains a variable tap in the form of a carbon brush that slides up and down the primary winding, which controls the secondary winding length, and hence the secondary output voltage is fully variable from the primary supply voltage value to 0 volts. Usually designed with a significant number of primary windings to produce a secondary voltage which can be adjusted from a few volts to fractions of a volt per turn. This is achieved because the carbon brush or slider is always in contact with one or more turns of the primary winding. As the primary core turns are evenly spaced along its length, then the output voltage becomes proportional to the angular rotation. Next will be a picture in the slide. We can see that the variac can adjust the voltage to the load smoothly from 0 to the rated supply voltage. If the supply voltage was tapped at some point along the primary winding, then potentially the output secondary voltage could be higher than the actual supply voltage. Variable auto transformers can also be used for the dimming of lights, and when used in this type of application, they are sometimes called thermostats. Variacs are also very useful in electrical and electronics workshops and labs, as they can be used to provide a variable AC supply, but caution needs to be taken with suitable fuse protection to ensure that the higher supply voltage is not present at the secondary terminals under fault conditions. And that will be it for auto transformer. So last but not least will be the additional/interesting facts about transformers. First, direct current cannot be used in a transformer because it does not produce changing magnetic field. Second, there are two types of transformer, the core type and the shell type. Transformers are employed for widely varying purposes, example, to reduce the voltage of conventional power circuits to operate low voltage devices such as doorbells. Fourth, the idea of transformers was introduced back in 1880, then in the year 1950, about 70 years later, there was an introduction of 400 kilovolt electrical power transformer in a high voltage electrical power system. Then in early 1970s, a large unit rating of 1100 megavolt amp was produced before 800 plus kilovolt class transformers started to be manufactured 10 years later in 1980. Last would be Otto Blathy Mixadari Karli Zipernowski of the Austro-Hungarian Empire first designed and used the transformer in both experimental and commercial systems. Later on, Lucien Guillard, Sebastian Ferranfi, and William Stanley perfected the design. That will be it, and this is the end of the slide and also the end of the presentation. So thank you for watching and Selamat Hari Raya.